This video is about logarithmic functions, which is the inverse of exponential functions. So we're talking again about y equals x and the mirror image. So an exponential function looks like this when we graph it, and a logarithmic function, when you graph it, looks like this. So I made a video first on inverse functions, so we understand what an inverse function is and how to find it. So we switch the x and the y, and then we solve for y, and that's how you get an inverse function, which is always the mirror image over this line y equals x. So I made that video first, and now I want to talk about logarithmic functions, which are the inverse of exponential functions. So if you had an exponential function like y equals 2 to the x, and this would be the graph here, you want to find its inverse, you switch the x and the y, so you get x equal to 2 to the y. The problem with exponential functions is once you switch the x and the y, and then you try to solve for y, we have no mathematical way of solving for y. We have no way of getting this y as an exponent, so that it reads y equals, which is called function form. When we take Algebra 1, we learn y equals 2x plus 3. That's a linear function. It's in function form because you can plug in for x and get out a y. You could switch this around and have different forms. It'll still be linear, but this is called a function form. Just like when we do quadratics, we say y equals x squared. That's in function form. So you always kind of want to have y by itself so that when you plug into your table for x's and y's, you can see the y values each time you plug in an x. So when you look for an inverse function, you switch the x and the y, and then you solve for y. But we have no way of expressing this as y equals. So that's where the term logs come in. So someone came up with the notation y equals log base b of x. This is logarithmic notation for expressing this, getting y by itself. So in this case, the base is 2. You would say y equals log base 2, b standing for base, of x. So I've got y by itself, and we use this function. So it's 2 to the y power equals x, which is what it says here. So this is the notation for this. It's a little tricky. It's a little strange. And then the graph of x equals 2 to the y is this here. I talked in the previous video about the domain of one being the range of the other. We know in this function right here, this exponential function, if I plug in 0 for x here, I get 2 to the 0, which equals 1, and I get this point right here. In this function, if you plug in 0 for y, you get 2 to the 0, which equals 1, and you get this point right here. So you can see that the domain of one is the range of the other and vice versa, and you can also see the mirror image happening here. So this is what we're talking about when we talk about logarithmic functions, except every function we've ever seen has been in the form y equals. So in order to express this as y equals, we use this logarithm notation. So let me look at some examples of things written in logarithmic form. So if you had something like 2 to the third power equals 8, you would write that as, this is your base, so you'd say log base 2, the answer, the y that we're solving for, is your exponent. So the exponent here is 3. So this is what it would look like. This is exponential form. This is logarithmic form, saying the same thing, but we read it as 2, base 2, to the third power equals 8. Okay, so you're going to be asked to go from exponential to logarithmic and vice versa. If you were given in log form, something like, I don't know, log base 3, I'll say 81 equals 4. If this is in logarithmic form, if you asked to express this in exponential form, you would say 3, the base, to the 4th power equals 81, which we know is true because 3 times 3 times 3 times 3 is 81. Some other things that you'll see solving logarithmic equations, something like this: log base 2 of 32 equals 3x. Again, this is in log form. If you were to translate this and switch it over to exponential form, you're saying base 2 raised to this power, whatever the log equals is always the power, 3x equals 32. In order to solve this, we've done some of these in class. In order to solve this, you have to have the same base. 32 is 2 to the 5th power. This is 2 to the 3x. Now that they have the same base, you can set the exponents equal to each other. 3x equals 5. Divide both sides by 3, and you get x equals 5/3. And you can see that that's true because if you plugged 5/3 in for x right here, the 3's would cancel, and you'd get 2 to the 5th equals 32, which is true. So that's a logarithmic equation, specific equation. There's no y here. It's not, you're not solving it's not a function. It's an equation. And let me do one more. Log base 4 5x plus 1 equals 2. If you translate this to exponential, this is your base 4 raised to this power of 2 is equal to 5x plus 1, and this is easy to solve because we know that 4 squared is 16 equals 5x plus 1. Subtract 1 from both sides, you get 15 equals 5x. Divided by 5, x equals 3. And if you plug 3 back in up here, you get 5 times 3 is 15 plus 1 is 16. So this reads 4 squared is 16 because that's your base and that's your exponents. So these are logs. We're going to look a little bit more at equations like this, solving equations. And again, the graph of a logarithmic function is the inverse of an exponential function. And that's an overview of logs.